At 3:47 in the morning, the Rotary platform begins to turn. It has not stopped since yesterday. It will not stop tomorrow. In northwest Indiana, where flat fields stretch toward a horizon broken only by silos and tank farms, the first shift is already underway before the nearest town wakes up. The air smells of fresh milk and cut grass and something older beneath it, earth, manure, biological process running on a scale that makes the senses recalibrate. Fair Oaks Farms spans thousands of acres. It holds approximately 36,000 dairy cows across multiple facilities. It produces more than 300,000 gallons of milk every single day. The tanker trucks that leave this property before dawn will reach processing facilities within 48 hours, and by the time a family in Chicago pours a glass at breakfast, the chain of events that produced it has already begun again. This is not a farm in the traditional sense. It is a closed system, a machine with living parts. And it runs, in significant measure, on the waste it generates. The story of how that happened, how a dairy operation of this scale converted biological byproduct into kilowatt hours and fed electricity back to the grid while simultaneously processing milk for hundreds of thousands of customers, is a story about engineering, about agriculture at its outer edge, and about what it takes to sustain something this large without collapsing under the weight of its own logistics. It begins, as most large things do, with a problem that wouldn't go away. Manure is not a new challenge for dairy farmers. It has never been. A single dairy cow produces roughly 65 pounds of manure per day. Multiply that by 36,000 animals, and the number reaches beyond 2.3 million pounds daily. In a small operation, that waste flows into a lagoon, breaks down over time, and eventually becomes fertilizer spread across fields. The system is imperfect, but manageable. At scale, it becomes something else entirely. By the mid-2000s, a large concentrated animal feeding operations, CAFOs, faced increasing regulatory scrutiny over methane emissions and groundwater contamination risks. Manure lagoons release methane continuously. Methane is a greenhouse gas more than 80 times as potent as carbon dioxide over a 20-year window. A 36,000 cow operation left unaddressed on this front would be emitting at a level that drew attention from regulators, environmental groups, and increasingly from the farm's own long-term economic projections. The conventional approach was containment and compliance. Build bigger lagoons, monitor more carefully, spread more strategically, stay within permitted thresholds. Fair Oaks took a different calculation. If manure produces methane and methane is fuel, then the problem contains its own solution, provided someone builds the infrastructure to capture it. The biogas system at Fair Oaks did not appear overnight. It required years of engineering work, capital investment, and operational learning. The concept of anaerobic digestion, bacteria breaking down organic material in the absence of oxygen to produce biogas, primarily methane, was not new. Municipal wastewater treatment plants had used digesters for decades. Agricultural biogas projects existed in Europe, but scaling that process to match the throughput of one of the largest dairy operations in the United States required a level of engineering specificity that pushed into territory with few precedents. The digesters at Fair Oaks are massive sealed vessels. Manure flows into them continuously. Inside, in carefully controlled anaerobic conditions, microbial communities break the organic material down. The process takes time, typically 15 to 30 days for complete digestion, and produces two primary outputs. The first is biogas, a mixture roughly 60 to 65% methane and 35 to 40% carbon dioxide, along with trace amounts of hydrogen sulfide and water vapor. The second is digestate, a nutrient-rich liquid and solid fraction that retains the fertilizer value of the original manure without the same emission profile. Both outputs matter. Neither goes to waste. The biogas, once captured, moves through a cleaning process. Raw biogas contains impurities, water vapor, hydrogen sulfide, siloxanes, that damage engine components if burned directly. A system of scrubbers and filtration equipment strips the gas down to a cleaner methane stream before it reaches the generators. The hydrogen sulfide alone, if unchecked, would corrode metal components within weeks. The cleaning systems run continuously, monitored by sensors that flag composition shifts before they become mechanical problems. What comes out the other side of the cleaning process fuels engines designed to run on natural gas. At Fair Oaks, those engines drive generators. The generators produce electricity. That electricity powers the farm's operations, the milking parlors, the cooling systems, the ventilation and lighting across multiple barn complexes, the water heating systems, and the processing equipment. The load is significant. Running a milking operation at this scale 24 hours a day requires continuous electrical draw. Cooling milk from body temperature, approximately 101 degrees Fahrenheit, down to 38 degrees within 30 to 60 minutes of collection, demands sustained refrigeration capacity. Fans, pumps, conveyors, lighting systems across facilities housing thousands of animals. The cumulative electrical demand is considerable. The biogas system at Fair Oaks generates enough electricity to cover a substantial portion of those operational needs. Beyond internal consumption, excess generation feeds back into the regional power grid. The farm effectively functions as a small power plant, one fueled entirely by what its animals produce. The closed-loop framing is not metaphor. Waste becomes fuel. Fuel becomes power. Power runs the operation that produces more waste. The cycle is not perfectly closed. Inputs of feed, water, and veterinary supplies enter from outside, and finished milk and digestate exit. But the energy loop within the system operates on a logic that conventional dairy farms do not approach. To understand why the milking operation exists at this scale at all, it helps to trace the trajectory of American dairy over the second half of the 20th century. In 1950, the United States had approximately 23 million dairy cows on 3.6 million farms. The average herd was small, fewer than 10 cows. Milk yields per animal were lower than they are today, and the industry was distributed across the country in a pattern that reflected local markets and family labor. Over the following decades, consolidation accelerated. Larger operations could invest in equipment, breeding programs, and veterinary care that smaller farms could not afford. Per-cow milk production rose substantially as selective breeding and nutritional science advanced. The number of farms dropped while the number of cows per farm climbed. By the 1990s, operations with hundreds of cows were common. By the 2000s, the upper boundary had shifted again. Fair Oaks represents one of the endpoints of that consolidation curve. an operation large enough to justify infrastructure investments that would be economically impossible at smaller scale. The biogas system is one example. The rotary milking parlors are another. A conventional milking parlor requires cows to enter, be attached to milking equipment, complete the milking cycle, and exit. Throughput is limited by the number of stalls and the time each cow requires. At 36,000 animals needing to be milked multiple times per day, typically 2 to 3 times, the numbers become demanding. A 200-stall herringbone parlor operating at peak efficiency might process 800 to 1,000 cows per hour. Even at that rate, and milking 36,000 cows across multiple daily sessions requires either an enormous number of parallel parlors or a fundamentally different approach. The rotary parlor, sometimes called a carousel or merry-go-round system, addresses throughput differently. Cows enter onto a large rotating platform, typically holding between 60 and 100 stalls. The platform turns continuously at a rate calibrated to the average milking time per animal, usually between 8 and 12 minutes per full rotation. Workers or automated equipment attaches milking units as each cow's stall passes. The cow rides the platform through its milking cycle. When the rotation brings it back to the entry and exit point, the milking unit detaches and the cow steps off. The next cow steps on. The platform does not stop. The process does not stop. Throughput is continuous rather than batch-oriented, and the design allows a small number of operators to manage a large number of animals simultaneously. At Fair Oaks, multiple rotary parlors operate across the facilities. The specific configuration and capacity varies by barn complex, but the operational principle is consistent: continuous flow, high throughput, minimal downtime. At 300,000 gallons of milk per day, the math works out to roughly 12,500 gallons per hour, 24 hours a day, across the full production cycle. The cows themselves are central to every other calculation, and the management of 36,000 animals as a single integrated system requires a level of data infrastructure that would have been unimaginable on a family dairy farm of even 20 years ago. Each cow in a large modern dairy operation carries an electronic identification tag. That tag communicates with readers throughout the facility, logging which animal entered which parlor at which time, how much milk it produced in that session, and flagging any deviation from its individual baseline. A cow that produces 10% less than its 7-day rolling average triggers a health review. A cow that fails to approach the milking area on schedule generates an alert. The data accumulates continuously, and management software aggregates it into dashboard views that allow a relatively small number of people to monitor the status of thousands of animals simultaneously. Veterinary staff move through the barns on scheduled rounds, but the data layer means that many problems surface before they are visually apparent. Mastitis, inflammation of the udder, one of the most economically significant health conditions in dairy herds, often shows up first as a decline in milk output or a change in conductivity measured by the milking equipment. Early detection reduces both the severity of the condition and the likelihood that it spreads. Nutrition at this scale operates on a similar logic. Feed rations are formulated by nutritionists who balance energy content, protein levels, fiber fractions, and mineral supplementation against the production demands of different groups of animals. Fresh lactating cows have different requirements than dry cows preparing for their next calving cycle. High production animals in peak lactation require different energy support than lower producing animals. The herd is segmented into groups, each receiving a ration specific to their production stage, and those rations are mixed and delivered by automated total mixed ration systems that load, blend, and distribute feed on schedule. Water consumption at this scale is also notable. A high-producing dairy cow in peak lactation may drink 30 to 50 gallons of water per day. Across 36,000 animals, that represents an enormous daily water requirement, managed through a network of automatic waterers distributed throughout the barns and feeding areas, monitored for function and consumption patterns. The digestate produced by the biogas system closes a different loop within the farm's resource cycle. After the manure passes through the digesters and the biogas is captured, what remains is a liquid and solid slurry that retains the nitrogen, phosphorus, and potassium content of the original waste, the same elements that make manure valuable as fertilizer, but with a substantially reduced odor and pathogen load. The digestion process kills a significant portion of the bacteria and weed seeds present in raw manure, producing an end product that is more stable and easier to handle. The digestate separates into liquid and solid fractions. The liquid fraction, high in available nitrogen, applies well to cropland as a fertilizer substitute that reduces the need for purchased synthetic nitrogen. The solid fraction, once dried, functions as bedding material, a detail that closes the loop more tightly still. Across large dairy operations, bedding material is a significant ongoing cost. Wood shavings, sand, straw, all must be sourced, purchased, transported, and managed. Recycled manure solids, properly dried and processed through the digester to reduce pathogen load, replace a portion of that purchased bedding, returning the material to use within the same facility. The economics of biogas systems in agriculture are complex. Capital costs for digester construction, gas cleaning equipment, and generator systems are substantial. Large agricultural biogas installations can cost several $1 million per installation. Payback periods depend on electricity prices, renewable energy incentives, the cost of alternative bedding materials, and the avoided costs of more conventional manure management. At the scale of Fair Oaks, where the continuous manure stream is large enough to justify the infrastructure, the system economics support the investment in ways that would not apply to a 200-cow operation. The regulatory environment has also shifted in ways that make biogas systems increasingly attractive. Renewable energy credits, carbon offset markets, and EPA programs designed to reduce agricultural methane emissions have created financial mechanisms that complement the direct value of electricity generation. Fair Oaks has positioned itself within these frameworks, treating its biogas production not only as an operational resource, but as a marketable commodity with its own revenue stream. The milk itself, the primary product around which everything else is organized, moves through the facility on a timeline that compression and logistics keep very tight. Within minutes of leaving the cow, milk enters a closed pipeline system that carries it from the milking parlor to refrigerated bulk tanks. The temperature drops quickly and stays controlled. Bacteria growth in raw milk follows an exponential curve that temperature management interrupts, Every hour that milk sits above optimal temperature is an hour of accelerated microbial activity. At this scale, the cold chain is not optional. It is the margin between usable product and waste. From the bulk tanks, milk moves into tanker trucks. The trucks are dedicated to this route. They do not carry other products. They do not sit idle while other logistics sort themselves out. The 48-hour window from cow to processing facility is a hard constraint that the entire downstream supply chain is organized around. Drivers operate on schedules timed to keep that window intact across all conditions and all seasons. Processing facilities receive the milk, conduct quality testing, and move it into pasteurization, separation, and packaging lines. The scale of Fair Oak's daily output, 300,000 gallons, means that the processing facilities receiving that milk are themselves large-scale operations built to handle continuous, high-volume input. The logistical relationship between farm and processor is a designed system, not an improvised arrangement. The human workforce that operates Fair Oaks operates in shifts that mirror the farm's continuous production cycle. Dairy cows do not recognize weekends. Their biological rhythms require consistent milking intervals regardless of the calendar. Cows that go unmilked for extended periods beyond their normal schedule experience discomfort, potential health complications, and production losses. The operation runs 365 days a year, which means the labor schedule runs the same. Multiple shifts cover the 24-hour cycle. Each shift includes milking personnel assigned to the Rotary parlors, barn staff, managing feeding, and animal observation, a maintenance crews keeping mechanical systems operational, and veterinary and reproductive staff during day hours. A farm of this scale employs hundreds of workers in a range of roles, from the highly technical, nutritionists, veterinarians, biogas system engineers, to the physically demanding work of daily barn operations. Training is a continuous function. In an operation this large, the difference between a crew member who knows why a procedure exists and one who is simply following steps matters. A cow that shows early signs of illness, noticed by a barn worker who understands what to look for, costs far less than one that reaches a more advanced health state before being identified. The same principle applies across the operation. Whether it is a change in the Rotary platform's behavior that signals a mechanical issue or a shift in biogas output that indicates a change in digester conditions. The environmental footprint of a 36,000 cow operation is not small, and Fair Oaks does not present itself as having solved the environmental challenges of large-scale dairy farming. What the biogas system addresses, methane capture, is significant. What it does not address, land use, water consumption, feed production, remains. Producing feed for 36,000 dairy cows requires an enormous amount of cropland. Corn silage, hay, and other forages require acreage, irrigation in some cases, fertilizer inputs, and fuel for cultivation and harvest. The embedded environmental costs of feed production are substantial, and they sit outside the boundaries of the closed-loop energy system on the farm itself. Water use is similarly significant. Beyond what the cows drink, cleaning operations for milking equipment and barn surfaces require large volumes of water. Some of that water re-enters the waste stream and passes through the digester system. Some is discharged according to permitted limits. Managing the water balance of an operation this large requires active monitoring and continuous adjustment. These are not problems unique to Fair Oaks. They are structural features of large-scale industrial dairy farming that biogas systems address only partially. The renewable energy dimension is a genuine contribution, capturing methane that would otherwise enter the atmosphere and converting it to electricity has measurable environmental value, but it operates within a broader context that the farm's advocates and critics both acknowledge. At 4:22 in the morning, a tanker pulls out of the loading dock. The driver has a window to make. The milk in the tank left a cow less than 2 hours ago. The rotary platform continues to turn. The digesters process the previous day's manure through the same microbial chemistry they ran yesterday. The generators hum at their steady output, feeding power into systems spread across acres of barn space. Somewhere in the monitoring center, a display shows the biogas system running within normal parameters. Methane content in the cleaned gas stream, 62%. Generator output, within expected range. Digester temperature, stable. The numbers update every few minutes, automatically logged against the previous 24 hours for comparison. By 6 in the morning, the first shift of the day has been working for 2 hours. The second shift arrives at 2 in the afternoon. The third shift takes over at 10 in the evening. The cows cycle through the milking parlor according to the rotation schedule. Feed is delivered at set intervals. The biological clock of the herd and the operational clock of the facility run together in a rhythm that does not pause. 300,000 gallons of milk every day. The number is large enough that it resists easy mental representation. Laid out in a line of standard gallon containers, it would stretch across more than 56 miles. Converted to fluid ounces, it would fill roughly 38.4 million glasses. As a production figure for a single facility, it places Fair Oaks at a scale that few agricultural operations in the United States reach. The biogas system that runs alongside that production represents a different kind of number. Tons of methane captured per year, kilowatt hours generated per month, dollars of electricity cost avoided, carbon credits generated and sold. These are the numbers that the farm's engineers track, that investors consider, that environmental analysts assess. They are less dramatic than 300,000 gallons, but they describe a different dimension of what the operation has built. An energy system nested inside an agricultural system, each sustained by the other. The long arc of this project, from the initial decision to invest in biogas infrastructure to an operating system feeding electricity back to the regional grid, reflects a broader question that large agricultural operations have been working through for the past 2 decades. Whether the scale that creates environmental problems also creates the capacity to solve them. Small farms do not have the capital to build digesters. They do not have the continuous manure stream to justify the infrastructure. They cannot employ the engineers who manage biogas systems or the data systems that track herd health across thousands of individual animals. The consolidation of American dairy farming that made Fair Oaks possible also created the conditions under which a biogas-powered dairy could exist. That is not a comfortable conclusion for everyone. The same consolidation that enabled the renewable energy investment also displaced the smaller operations that couldn't compete on cost. The communities built around family dairy farming changed as the economics of scale shifted what was viable. The environmental benefits of biogas capture at Fair Oaks exist in a context shaped by those changes. The farm continues to operate. The platform continues to turn. The generators continue to run on fuel produced by the animals producing the milk that fills the tanks on the trucks heading down the highway before most people are awake. At 300,000 gallons per day, the operation does not slow for consideration. It runs because it has been engineered to run continuously at scale on a closed loop of biological process and captured energy that converts one of agriculture's most persistent waste problems into one of its most productive resources. That is the story of Fair Oaks. Not a triumph to be declared, not a solution to be celebrated without qualification, a system running before dawn every day. If this look inside one of the most ambitious large-scale dairy operations in the country gave you something to think about, hit the like button and let the algorithm know it matters. Subscribe if you want to keep following stories about the industrial systems that sit just behind everyday products. Stories about scale, engineering, and the logistics of moving food from the source to your table. Drop a comment and tell us where you're watching from. These stories reach people we don't expect, and that's always worth knowing.